In the second part of step 17, we're going to focus on solving exponential equations. So far we've just graphed them and we've done some transformations with them, but now we're going to solve exponential equations. An exponential equation is very similar in solving other equations in a sense that we're still trying to get x, the variable, by itself. It's different though because x is trapped up in the exponent right now. So we can't simply add 2, divide by 2, simple techniques that we've used in the past. We need to actually adapt a new method. The way we're going to do that, we're going to try to express each base as the same base. So currently we have 2 to the x, 8 to the third. We want these to be the same number. 2 is already very simple, but 8 could be expressed as another number raised to a power. And to help you decide which number we're going to use, I have this chart for you. If we look over here in our chart, we find 8 right here. 8 is simply, if we look at it this way, it is simply 2 raised to the third power. That's another way to write 8 is 2 to the third power. So on the left side, we're not going to do anything. It's still 2 to the x. On the right side, we're going to take out the 8 and replace it with 2 to the third. Now, applying the properties of exponents, we have the power to a power rule. That becomes 2 to the 9th. Once you have each side expressed as the same base, we can remove the bases and just set the exponents equal to one another. If 2 exponential expressions have the same base, then their exponents are also going to be equal. Therefore, x equals 9. Now we can check it. We should always check our work. Is 2 to the 9th the same thing as 8 to the third? To do this, let's use our calculator. 2 to the 9th is 512. 8 to the third is also 512. So we know that we are correct. Take a look at the next option, the next example. Again, we're still trying to express these with the same common base. So we go to our chart again. We see that 3 is a pretty simple base. 9 could be expressed as some other number raised to a power. 9 is right here. It is 3 squared. 3 squared. So we're going to rewrite what we have. We're not changing the right side. On the left side, however, we're going to take out that 9 and replace it with 3 squared because 3 squared is 9. Next, we're going to rewrite it 3 to the 2 times 2x minus 1, just another way of rearranging our parentheses. And then we distribute 3 to the 4x minus 2 equals 3 to the 6x. Notice we now have each side of our equation with the same base. Therefore, we can set the exponents equal to one another. 4x minus 2 equals 6x. Solving by subtracting 4x from both sides. I have negative 2 equals 2x, and dividing by 2, x equals negative 1. Go ahead and pause the video and try these next two examples. Notice in the first example, 64 is the same thing as 4 to the third power. Once I have the same base, I can set the exponents equal to one another and solve. In the next example, 125 is just 5 to the third. Once I have the same base, I can set the exponents equal and solve. Let's take a look at a real-world example. When we do all of these real-world problems, we're going to be starting with our exponential function y equals a b to the x, where y is our ending amount and a is our starting amount. B is the base by which it's changing, or the rate at which it's changing, and x is typically going to be representative of time. So in this example, Kristen starts an experiment with 7,500 bacteria cells. That's what we're starting with. After 4 hours, that's our time, there are now 23,000 cells. That's what we end with. So the first thing they want us to do is to write an exponential function that could be used to model the number of bacteria after X hours if the number of bacteria changes at the same rate. So we need to have a Y and an X, but we need actual numbers for A and B. So let's take our information that we're provided and substitute. I'm going to take out Y and put in 23,000. I'm going to take out A and put in the starting amount, 7,500. I don't have a number for B right now. It doesn't tell me if it's doubling or tripling or increasing by 12.5% per hour, so I just put a B. But I do know that X is 4. From here, we can actually solve for B. We're going to divide by 7,500 on both sides, because I need to get B by itself. Let's use our calculator. So we'll take 23,000 and divide by 7,500. That gives me 3.067. But that doesn't tell me what B is. I need to take the fourth root of B to get rid of the fourth power. On the calculator, we're going to press Math, option 5. We want it to be the fourth root of 3.067. That's approximately 1.32. We'll even have 3 decimals, 1.323. Now that I finally have my B value, I can go back to my original problem. I know what B is. B is 1.323. I also know what I'm starting with. I'm starting with 7,500. So this is my exponential function that models this example. Now I can take this same exponential function and I can use it to predict how many bacteria cells we would expect there to be after 12 hours. Instead of X for the unknown time, I'm going to replace it with 12 for 12 hours. And again, using our calculator, we'll type 7,500 parentheses 1.323 close the parentheses, raise it to the 12th power. And it's approximately 215,664. Since I'm estimating and rounding, we'll use the squiggly equal sign. And there we have it. Let's talk a little bit about compound interest. A lot of times when we're talking about exponential functions, it's dealing with money and compound interest. This formula is not much different than the formula we were just using, y equals a b to the x. We still have our ending amount, we still have a starting amount. The rate portion, part that was formerly our b, is going to look a little more complicated, but there are similarities between the two. In this formula, a is our ending amount. That's the amount we end with. P is our starting amount. It's called the principal. We always start with the principal amount. That's our starting amount. Or the amount of money we start with. R is going to be our rate. We've seen that in other examples. The percentage of the interest rate. Something new is something called the n piece, the n variable. These are the number of compounding periods in a year. So for instance, if it says that this happens monthly, how many months are in a year? 12. If it happens daily, how many days are in a year? 365. You might see bi-monthly. That's twice a month, so 24 times a year. It might happen annually, which is once a year. Those are just some of them that you're going to encounter. T is still going to be representative of our time in years, because it says T years. So if it asks us for 6 months, T would equal 1/2. If it asks us for 3 months, T would equal 1/4, because 3 months is 1/4 of a year. All right, let's start with our original formula. A equals P 1 plus R over N to the NT. And we're going to replace it with all the information we have in this problem. The first thing I come across as I read is 4.2%. That's the rate. Remember, we always write it as a decimal so that we don't have to use the percent sign. Compounded monthly. That's our next keyword. That means that N is going to equal 12. This was my rate. That's my monthly. 2,500 is invested. 2,500 is what I'm starting with. That's what I'm putting into the account. So that's going to be our principal. And then it says, what will be the balance after 15 years? 15 years is my time. So they give us all the information we need. Now we can take out the pieces of our formula and plug in the 4 pieces that we know. I'm going to take out R. I'm going to put 0.042 in its place. I'm going to take out N and write 12. Since I already I'm going to replace t with 15. And finally, I'm going to replace p with 2,500. Let's take a look at what this will look like on our calculator. First, we'll type 2,500. Alpha y equals 0.042 divided by over 12. Close the parentheses. And we're going to raise that to the 12 times 15 power. And we end up with approximately $4,688.87. In fact, since this is a rounded number, I should use my approximation symbol, not just an equal sign. The last thing we want to look at is how to solve when we have an inequality. We're going to treat this very similar to when we had exponential equations. We still are going to keep our two sides separated, and we want to express each number as a small base raised to a power. 16, again, you could flip back all the way up to your chart if it helps. 16 is just 4 squared. There's a 16, but there's another 16 over here. It's 2 to the 4th. 16 is 4 squared, and 16 is 2 to the 4th. I'm always going to try to use the number or the version that has the smallest base. 2 is smaller than 4, so that's the one I'm going to use. I also like that one because the other term that we're dealing with, the other base, is an 8, and I can use 2 to the 3rd for 8. So let's go back to what we had here. 16 is 2 to the 4th to the 2x minus 3, and 8 is 2 to the 3rd. Again, rewriting this and distributing. Once I have the same base on both sides, I can just take the exponents. And I'm not going to set them equal. I'm going to keep that same symbol, which is less than. I'm going to add 12 to both sides, and I'm going to divide by 8. So x is less than 15 over 8, or just yet. When you have a fraction, sometimes it's nice to think about our exponent properties and rewrite it with a negative exponent. Now you might say, why would we want to do that? Well, when we are dealing with numbers of bases, we don't want to have to deal with any fractions. I'm going to take lead from the number on the left. The base on the left is a 3. So I'm going to go to my chart and see if 3 to some power is 243. Going back to my chart. Let's get rid of some of the work that we've done before previously. Remember, I'm trying to express it as a power of 3. There we have it. 3 to the 5th is 243. So going back to the problem we're working on, 243 is just 3 to the 5th. Using the power to a power property, 3 to the 2x minus 1 is greater than 3 to the negative 5. Notice that the bases are equivalent, so I can just drop the bases and compare the exponents. The exponent on the left is greater than the exponent on the right, or equal to. And now we solve. We add 1 to both sides. We divide by 2. I don't need to flip my sign because I'm dividing by a positive number. And that's my answer. Go ahead and pause your video and try 4B. Notice that first I brought 32 back up into the numerator by raising it to a -1. I know that 32 is 2 to the 5th, so I substituted. Once I had a common base on both sides of my inequality, I set the exponents compared to one another. The left one is greater than the right one, and I solved.